about this carefully, you can cool it down until slightly below the melting point. So you can create a supercooled liquid which is metastable. And then if a nucleation event happens, a crystal will grow. And actually what they do here is, you see here is the end of a little glass tube. They, on purpose, they nucleate the crystal here. It's growing through the tube, and then it's emerging into this liquid. So for a theorist, this is as close as you can get to the growth of an isolated crystal in a homogeneous undercooled melt. Okay? So this is a pure substance. And why can you see these pictures? It's because it's a transparent substance. Actually, there is a few organic molecules that are transparent, but that crystallize just in the same fashion as metals. So they have a cubic crystal structure, and they have rough, microscopically rough solid-liquid interfaces. So the structure that you see emerge here is very similar to what you would see in a metal, but you can just watch it under a video camera. Okay? Now, I said that this experiment is conceptually simple. Actually, to do it in practice is very difficult. And for one reason, well, you have to carefully control temperature and the purity of the substance and all that stuff. And there is a second reason. Well, you see, here, this is a pure substance. And we are very close to the approximation that I have made, namely the density is approximately the same in the two phases. Since it's a pure substance, the only extensive quantity that is different between solid and liquid is the internal energy. So this growth process is limited by the flow of heat, because when the liquid crystallizes, the latent heat is set free, and this heat has to be evacuated. So what happens, the crystal grows, and it brings its interface up to very close to the melting point. As Abik has mentioned, the Gibbs-Thompson equation tells us that up to some curvature effect, the temperature should be equal to the melting temperature. So close to the crystal, we are at the melting temperature. Far from the crystal, we are undercooled. So there is a temperature gradient that goes from the crystal away to the liquid, which generates a heat flux from the crystal to the free space. And this allows the crystal to continue to grow. Well, that means that you will develop temperature differences between the vicinity of the crystal and the far away fluid. And when you say temperature differences, you say in reality there is a very slight density difference, and this will trigger convection. And so if you want to be in this limit that I have considered, where only diffusion is important, well, you have to take away convection. And the only way to really do this is to do this in microgravity. So these pictures are actually taken from space experiments. So this experiment was done on board of the space shuttle somewhere in the beginning of the 90s, if I'm not wrong. So actually, these pictures are very, very costly. But why is this important precisely? Because this problem has been studied a lot by physicists and mathematicians. So it's very important to test these theories with experimental data that are as good as possible. So you can do that for this sort of relatively slow growth in microgravity experiments. We'll also see there are other experiments on extremely fast growth, where you put yourself in an electromagnetic levitation facility. So you study very little metal droplets that you heat with very strong alternative currents. So this creates a levitation force, so you can hold them over a magnetic coil, sort of in levitation, so you can avoid any contact with container walls. So heterogeneous nucleation is suppressed, and so you can undercool them by 100 or 200 degrees, and then growth happens very rapidly. And so in this regime, you can also compare, because their convection also is not important. Okay? So we have these different regimes, very slow growth, where the undercooling is a fraction of Kelvin. Typical growth speeds are of the order of microns per second, and tip radius here is about microns. So this is observable with optical resolution, and here very fast growth. And so what's the experimental observation? So you have the crystal that emerges from this tube, starts to grow. You see it develops main branches with side branches. And what you observe that after some transient, this tip settles down to a constant speed. So it propagates linearly here with a constant speed, and this speed is only a function of the initial temperature of the melt. Of course, it depends also which substance you use, but for a given substance, the growth speed is a unique and reproducible function of the melt temperature. So this is an easy data that one would like to reproduce with a model. Okay? Now I have written down you in the first part the free boundary problem, which is the traditional formulation of this problem. So here's the Stefan condition, as I mentioned here. What limits the growth is the evacuation of heat. So here you have the currents that come from the solid and the liquid. That's the Stefan condition that we had. Here's the Gibbs-Thompson condition that I have discussed at length, that we have seen before. And we said that heat is propagating by diffusion. So I write this diffusion equation for the temperature, and it's the ordinary diffusion equation. Now, just to mention, as you have seen, a dendrite here, of course, is an anisotropic structure. You see that the main branches grow as along the axis of a coordinate system, and that's because the crystal structure is cubic. So where does the anisotropy come into play in this free boundary problem? Actually, it comes into play through the interfacial properties. Because if you have a crystal, and if you have the crystallographic direction, if you cut a surface, you can easily imagine that the surface energy and also the surface mobility might depend on the direction in which you cut. Because if you cut like this, it's a closed packed plane. If you cut like this, it's a miscut surface. So the surface energy will be slightly different. And indeed, so the quantities that will vary with the orientation n is the surface energy here and the mobility here. So both of these quantities come in the Gibbs-Thompson condition. Okay? So here the anisotropy comes into play. For most of the following, I will just forget about it in order to simplify the presentation. But be aware of the fact that anisotropy comes into play here. So I will analyze a particularly simple case of this model in which I will assume that a lot of properties are the same in solid and liquid. So this is called the symmetric model. So it has been studied by theorists quite a bit. So you assume that the diffusivity is the same in both phases. You assume also that the specific heat is the same in both phases. Then the specific heat largely falls out of the equations. And you define a dimensionless temperature field like this. It's the difference of the temperature with respect to the melting temperature divided by this ratio of latent heat and specific heat, which has the dimension of a temperature and which is a material-specific parameter. Okay? Once you have done that, well, you can rewrite the equation in this way, where you have only 3 parameters left. It's the diffusion coefficient here. You get this quantity normally called d naught, which is called the capillary length, which is proportional to the surface tension here and to thermodynamic quantities. So this also is a material-specific quantity. It's set. It's a given value. And then here, this is a variant of this interface mobility mu k that I have defined. So it's called the kinetic coefficient. It's like the inverse of this mu k. Okay? And so in this, with these quantities, the Gibbs-Thompson condition becomes particularly simple. It's minus d naught times the curvature, minus beta times the velocity. Okay, so this is what the mathematicians call the Stefan problem. As I've already mentioned, this was formulated more than 100 years ago. And so especially mathematicians have worked a lot on this. And they have proven a lot of things. In particular, they have proven that this is a well-posed problem and that there exists a solution. So, okay, we can go about it. And then you can imagine how one would solve this mathematically. So in this formulation, what do you do? Well, if I go back to the previous picture, suppose that you have a given shape of the crystal and you know the interface velocity from the previous time step. Then you can plug this in here. So you can calculate the boundary condition for the temperature at the interface. Next, with this boundary condition, you solve the diffusion equation. Okay. Once you have the solution of the diffusion equation, from this you can calculate the heat current that comes to the interface, and then you get a new value of the interface velocity, and then you move the interface forward and you start over. Okay? So this would be the traditional way of solving this type of problem. Now, why is it of value to have this formulation? It's that in some special cases you can find analytical solutions. So for example, what has been studied is the motion of a planar interface, the motion of a needle crystal, the growth of a sphere, or things like that. You can completely study analytically with this formulation. Now, oops. Oh, I think I'm missing. Ah, no. Well, I changed the order of my slides. I'm sorry. Okay. Usually what I show next is, yeah, this here. Okay. So, as I said, it's of value if you want to do some analytic calculations. But why is it difficult if you want to calculate numerically a general case? It's because, well, you have to represent your interface somehow. So suppose your interface has not a simple shape such as a sphere or a cylinder or whatsoever. Suppose you want to calculate a dendrite, so you have some complicated shape. How do you represent the interface? Well, the traditional way is to put some marker points. That is, you have some points on the interface. Then you can approximate the interface, say, by a polygon. And then you can put this, say, in a finite element mesh. And then you can solve the diffusion equation on this finite element mesh. You can calculate the velocity for each segment. Then you can move the segments forward. Okay? But the problem is, of course, if you have something like dendrite growth and you develop new interface, then of course the points will move further apart, and at some point you have to add new points. And more generally speaking, from time to time you have to remesh your interface because the length changes. Also, if you have things like interface pinch-off, well, this is difficult because you have to decide which points go to which side of the pinch, and you have to define various sets of points that are the different parts of the structure. So you can easily conceive that writing an algorithm like this is quite complicated. Okay? Nevertheless, it has been done. There is many examples for such sharp interface codes in 2 dimensions. If you want to do it in 3 dimensions, it becomes really hellish. Because you have to have a 2-dimensional surface mesh that goes over your 2-dimensional surface and that evolves in 3D. Mathematicians like to work on such problems, but you can keep a PhD student busy just to study the meshing algorithm, right? I mean, that's a job for mathematicians, but not for physicists or material scientists. So that's where the idea of the top-down approach with the phase field model comes in. The idea is, instead of having such an explicit representation of interfaces, you can think about an implicit representation of interfaces, meaning, okay, we introduce an additional function, which is called the phase field, because it will indicate in which phase we are. And that has one value in one phase, the other value in the other phase, and that varies through the interface in such a smooth manner. And then the interface will be just the point at the center of the interface here. So it's this black line, which is a level set of this phase field function. And so if we want this interface to move, we need to find an equation of motion for phi, because you can easily see, for example, if phi increases here, that means that the interface moves forward. So in order to properly describe interface motion, we need to give an equation of motion to this field phi, and if we find the good equation of motion, then we can describe the correct free boundary problem in this way. Okay? So that's the basic idea. I would like to state that phase field is not the only model of this type. There is, for example, what is called the level set method, which works with the same idea. They introduce an auxiliary field that they have involved in time, and the the interface is represented by a level set of this function. Only this function is constructed purely mathematically. It's a distance function. Whereas, for me, the beauty and the advantage of the phase field method is that we will base this evolution equation for the phase field phi on physics. Okay, now I go back because why is this so slow? Okay, sorry. Yes, because as physicists, precisely we know that this description of interfaces by sharp surfaces, that's a macroscopic point of view. But you can look at interfaces at various scales. And so if you look at it really at the atomistic scale, here's as promised, here is the a molecular dynamic simulation of a solid-liquid interface. So this is a three-dimensional sample, but it has a few atomic layers thickness. So in the solid, the structure is ordered, it's cubic. So since all the atoms are in one row, you can sort of view through it. So here you have an ordered structure. In the liquid, well, it's difficult to see by eyes, but the density is almost the same, but it's a disordered structure. And you see that the order doesn't disappear. All of a sudden, there is a sort of intermediary region where it's partially ordered. For example, here you can still see something like a layer, but it's much more diffused than here. And well, so you can easily conceive that there is a coexistence between an ordered and a disordered structure, and that this order disappears gradually. Okay? So this idea of having a diffuse interface can be rooted in this physical description on the microscopic level, because even though I have told you before that, well, the solid-liquid transition doesn't have a critical point, you can still define an order parameter. Okay? For example, people that do molecular dynamics, they can detect in some sense whether they are in a solid and in a liquid. How they do that, they call what is called the bond angle order parameter. So they sit on one atom and they look at the nearest neighbors and they look at the angles that are between nearest neighbors. If you are in an ordered structure, these angles are always approximately the same. Whereas in the liquid, you can have any value. So you take, in some sense, the variance of this angle distribution, and you get an order parameter. Okay, so there is well-defined procedures of doing so, and you can define a function that takes one value here and the other value here, and has a gradual variation through the interface. You can also analyze these things with classical density functional theory. That is where your variable is the local density, that is the probability of finding an atom somewhere. In the solid, this probability will oscillate. It will be maximal on the position of the atoms and minimal in between. In the liquid, it will be homogeneous. So you can write down a free energy functional in this language, and you can show that actually the interface energy can be well described by a sort of Ginzburg-Landau functional. Okay? So a Ginzburg-Landau functional is reasonable for the description of such an interface, even though formally there is no Landau expansion or critical point to define. Okay? And this is a transparency that sort of echoes what I have already said in the beginning of the course. So what we have done up to now is to start from a microscopic point of view and going upward. So what we want to do now is to do the I'm not sure I did anything. Maybe I touched the cable somewhere. Yeah. Okay. So now we want to do the opposite, and we want to go top down. That is, we start from the boundary problem, and we want to get out okay, so how do we do that? Well, in some sense, what we want to do is we want to use the phase field as a toolbox. I mean, what we have done so far as a toolbox to implement this. So first of all, well, maybe I am going to write down here what I have already written before. In the classic sharp interface description, you would write down the free energy in the way that I have already written down before. You integrate over the solid domain the bulk free energy of the solid, over the liquid domain the bulk free energy of the liquid, and then you have the surface energy here, and you integrate along this. So we have to find ways to represent these contributions in the phase field language. So we'll start with the interface free energy, and of course we have seen how we can do that. Well, we want to describe the interfaces with the phase field, so we write down a free Ginzburg-Landau free energy functional with a double well function dw, and with the two constants k and h that we have had all the time. Here I've taken w like Guru did yesterday, with equilibrium values of the phase field that are equal to 0 and 1. And then we have seen, and you have found in your tutorials, that we can find the interface thickness and the surface tension by combinations of these two coefficients. Okay, I can write the surface tension actually as this combination of coefficients times quantity I that is a pure number, and that you have calculated now for several models. So the value of that number depends on the choice of the double well potential, but it's always a number of order unity. The important thing are here the scaling parameters k and h. So we know how to set the surface part. Now we need to look about the bulk part, because this here, of course, is a description of equilibrium interfaces. So here I have the wells that are exactly at the same height. So this would correspond to the case of the magnetic model with zero magnetic field, or to the case of the two-phase equilibrium without the thermodynamic driving force. So now we need to include the thermodynamic driving force. How can we do that? So as I said, what I have just given you, the interfacial part, this would be the free energy of the system at the melting point. So now we have to extend this free energy to other temperatures than the melting temperatures. And since we are interested generally in the vicinity of the melting point, I can just write a Taylor expansion. I can say the free energy is equal to the one at the melting point, which will be the interfacial part, plus this derivative times T minus Tn. Okay? So this is very similar to what we have seen just a while ago in the sharp interface problem, because we know that the derivative of the free energy density is the entropy density. We know that the entropy is different in the solid and in the liquid, so we need to interpolate them somehow. Okay? So I have introduced here an interpolation function g of phi, and the properties of this function is that its value at 0 is 0, and its value at 1 is equal to 1, which means that for phi equal to 0, the entropy is that of the liquid. For phi equal to 1, the entropy is the one of the solid. Okay? And I also require that the derivative of this function of at 0 is, and at 1 is 0. And this, I will come to this, back to this just in a second. So you see, this is an interpolation of the entropy, and I can put this here, and I get a closed expression of the free energy in terms of phi and t. Now, what's the role of this function g? Well, so generally speaking, if I have a non-zero term here, as I have mentioned, it's a non-zero driving force. So it's just like a magnetic field, and we have already seen that the magnetic field tilts the double well. Now I include this function g because I would like this double well to be tilted, but I would like the minima to remain exactly at 0 and at 1. If I just put a linear term, if I would put here just phi instead of g of phi, that would be like the magnetic field. I would just tilt the well by adding a linear term. That means that the minimum would be slightly shifted with respect to 0 and 1. Okay. If I put a function with these properties, actually for no matter what value of this driving force, of the temperature, my minima are always equal to 0 and 1. And that's very useful for the model construction. Okay, so this is the phase field free energy. I just want to show you here that you can obtain exactly the same thing in a different way that is also very intuitive. So if I have this macroscopic free energy here, how can I write down a phase field representation? Well, actually I can do this quite easily. Here I had a solid domain, a liquid domain, and an interface. Now here in the phase field, of course, everything is continuous, so I will have a single integral. Now I put here the fs of t, and then here I need to put a function which will be 1 in the solid domain and 0 in the liquid domain. So here I put this g of phi, because precisely this is 1 when phi is 1, so in the solid, and it's 0 when phi is 0 in the liquid. Then I add the liquid of t, and here I put 1 minus g of phi. Okay. So it's the same thing. This function is 1 in the liquid domain and 0 in the solid domain. And then here I put this interfacial free energy, which this one has the gradient phi squared plus W. And we have already calculated this will give a contribution only in the interfacial region, because that's where the surface tension is located. Okay? Now, first, you can see if I take the derivative of this with respect to phi, what I will get, well, for the interface, I will get the standard interface solution. And here, if I derive with respect to phi, I will get g prime of phi. And here, the difference between the free energies, which is exactly the driving force. And if I derive with respect to temperature, I will see again that here I will get the df by dt. So I will get the entropy, and I will get exactly this interpolation for the entropy that I have written down here. Okay? So, and this is particularly interesting because what is the sort of hand-waving interpretation for this expression? Suppose that I have my solid crystal and my liquid in the sharp interface representation. Then my free energy is given by this expression. Now if you stare at this, actually what this is just I smear out this surface by replacing the mathematical line with this phase field profile. And you see that these two terms are an approximation of the bulk free energy, and these two terms, this term is an approximation of the surface energy. Okay? So in some sense, in this spirit, you can see the phase field representation just as a smoothing of the free boundary problem, where replace a mathematical line by a profile that has a finite distance. And you can already guess that the approximation is more precise when the interface is thinner, because then you get closer to this infinitely sharp interface. Okay? And so that's this top-down spirit. I start from the infinitely sharp problem and I smooth it out by going to this phase field representation. Okay? So now I need equations of motion. So first of all, the phase field. I told you it's an order parameter, difference between ordered and disordered structure. So is it conserved or non-conserved? It's non-conserved because in order to go from a disordered liquid to an ordered solid, atoms have only to move about a fraction of the atomic spacing. They just have to jump in the right place. So this can take place in a finite volume of liquid without transport of atoms. But there is one thing that is conserved because, well, if you change the crystal structure, you change the entropy. So this is linked to a change in energy. So we have to take into account energy conservation. Okay? So the phase field part is easy. It's a non-conserved order parameter. So we write down our favorite Allen-Kahn equation that we have seen many times. Now the equation for the energy is a little bit more complicated. Okay, I will piece together two parts. One part is this one here. This is the balance equation for energy, so it describes heat conservation. So the little e here is energy per unit volume. Okay, so it's the internal energy density. And it is given by the divergence of the heat current. Here the kappa is the heat conductivity. So this here is Fourier's law. The heat current is minus kappa times gradient temperature. And this is the divergence law. So this is the conservation law for energy. Okay, so this is one equation that I use. The second equation is the first principle. So you know that the internal energy can change by changes in volume or changes in entropy. Now I have supposed that the molar volume is constant, so there is no mechanical term. So the only thing that I have is the TdS. And as I have shown you before, the entropy actually is a function both of the temperature and the phase field, because I have interpolated between the solid and liquid free energy with the help of the phase field. So here I use the chain rule. ds is equal to ds by dt times dt plus ds by d phi times d phi. So that's just the chain rule. And now I only have to evaluate these partial derivatives here to get the result. So this one, ds by dt, is equal to, can be related to the specific heat. The specific heat is given by T times ds by dt. Okay? So I can replace this by C divided by T. And ds by d phi I have just to calculate from my interpolation that I made. Then there is an additional thing here. This heat conductivity can be written as the product of the specific heat and the diffusion constant for heat. And then what I get in total, what do I have to do? I have to divide this, all this by dt, and to combine it with this. In the end, what I get out is an equation for the temperature, which has the diffusion part here, and which has here a source term. Okay, the source term comes from what? It comes from this d phi here divided by dt. Okay? Now this equation is actually very intuitive, because how does the temperature change? It changes either by diffusion of heat or by this, and this is a source term that is due to phase change, because phi will only change where in the phase boundaries, and it is proportional to the latent heat. So this is nothing by the release of latent heat when the phase changes. Okay? So it's diffusion plus latent heat generation, very intuitive. The reason why I've gone through this whole stuff is to tell you that this equation can be completely rigorously derived from thermodynamics. There's no hole in there. Right? Okay, so this Allen-Kahn equation plus this equation for the temperature constitute our phase field model for a pure substance. So it's two coupled equations. I will simplify them somehow to get back to this dimensionless formulation of the free boundary problem. So first of all, I will divide through the whole free energy by the constant h, which will leave me with this. So here in front of the Laplacian, I directly get the interface thickness squared. There's no more prefactor in front of the double well potential. And here I will get dimensionless constant, which is a combination of all these constants here. And instead of writing it for the temp, so the equation for the phase field becomes just this, where the primes is the ordinary derivatives of the double well and this interpolation polynomial with respect to the phase field. And here is the dimensionless equation for the temperature. And all of these constants that appear here can be related to the previous model parameters. Okay, so the result is we have written down a phase field model which amounts to these two very simple coupled equations. Okay? Sort of Allen-Kahn equation. The only new thing that this is coupled now to another dynamic field U. Okay? In the magnetic model, U would be the magnetic field, so that would be a constant. Here now, U is a spatially varying function because it's the temperature. And this spatially varying function obeys another dynamic equation. But still, these are two simple partial equations. With the programming experience that you have, now it will take you, even on your own, it will take you half an hour to program this. Right? So you easily conceive that this is much easier than to write a sharp interface code. So on first sight, it looks very beneficial. But you should be cautious in some sense, because you should ask, well, but how can I relate the parameters of my phase field model to the physical parameters? Or in other words, how can I prove that this is the right phase field model to simulate my good free boundary problem? Okay, and here we come to a quite complicated subject that I will not go through in detail with you. I will just try to illustrate this with you, because you can exactly relate, at least in many cases, the phase field parameters to the physical parameters with the help of a mathematical technique that is called matched asymptotic expansions. Okay? So I show you the result here, and then I will comment on what it is. So this mathematical procedure gives you relations that relate the physical parameters, which are the capillary length d0 and this kinetic coefficient beta, to the model parameters. The model parameters are what? They are W, the interface thickness, this coupling constant lambda, and this relaxation time of the phase field. The physical parameters are d0 and beta. So here you see how d0 and beta scale as a function of these model parameters. So if you have a given d0 and beta, you can choose your phase field parameters in such a way as to match these physical values. Okay? Now, first, A1 and A2 are just numerical constants of order 1. It's like this integral I in the surface tension. Those will depend on the exact choice of the double well potential. And if you choose to work with M or with C, so with a phase field that goes between -1 and 1, or between 0 and 1. So these numbers depend on the details of the model, but they are always just numbers of order 1. Okay. No. No. As long as you have a double well, you will always get the same scaling, but with different constants A1 and A2. Okay. Now, what's the idea of matched asymptotic expansions? It goes back actually to this idea of seeing the phase field as a diffuse interface representation of a sharp interface problem. If you look at this, so you have a coupled set of equations, the phase field and the diffusion equation. You can easily see that they behave very differently in different space regions. Because if you're away from the interfaces, then the phase field equation is trivial, because you have either that phase field is 1 or phase field is 0. No gradients, no time evolution. So outside the interfaces, you can forget the phase field equation. So outside the interfaces, you have just to solve the diffusion equation. Inside the interfaces, the thing is complicated, because you have this coupled nonlinear problem. So what you do is, it's the same thing what in mechanics you sometimes call boundary layer calculation. So you analyze your problem on two different scales. One, you place yourself at what is called the outer scale. In the outer scale, you forget about the phase field, you solve the diffusion equation. And then you do a second calculation on what is called the inner scale. That is, you look at the problem at the interface scale. At the interface scale, the variations of the phase field are important. But on the other hand, the variations of the diffusion field are small, because the diffusion field varies on the scale of the outer region. Okay? So you can treat the variations of the diffusion field U as a small perturbation on the equilibrium state of the phase field. Okay? And if you look at the scale of the interface, there's also many other things that are constant. For example, as you see along this structure here, the radius of curvature varies. But if you look locally on the scale of the interface, it's like as you have a constant curvature. Also, the interface speed will certainly vary along the structure, but if you look at the local piece of interface, this speed will be approximately a constant. So the idea is what? You do this inner calculation on the phase field as if it was a constant curvature and a constant normal speed. And you treat the forcing by the outer field as a small perturbation. In this limit, you can get an approximate solution for the inner problem. And then this inner problem, you match to the solution of the outer problem. And by this way, you will obtain what this phase field equation imposes on the outer field. Okay? I know this might be a little bit abstract, so I've put up a little illustration for you. So this is what? This is just a one-dimensional problem. So you have an interface that is advancing, and if this advances in a melt that is undercooled enough, that is where U goes to a value that is below -1, far away from the interface, then you can quite easily show that there is a steady state solution. The steady state solution in the sharp interface problem, in this case you can exactly solve the sharp interface problem. You find that the solution is that the temperature is constant behind the interface and that there is an exponential profile before the interface. And this exponential profile has a characteristic length scale which is given by d by v, diffusion constant divided by the velocity, which is called the diffusion length. So in this problem here, the outer scale is the diffusion length. So here I have plotted the solution of my phase field on this outer scale. So here I scale the space variable by the diffusion length d by v. So what you see is here you see the exponential profile of the temperature. And on this scale you see that the phase field almost looks like a step function. Okay? Because the diffusion length is much larger than the interface thickness. So this is the usual hyperbolic tangent solution, but it looks like a step function because it varies on a scale that is much smaller than the diffusion length. Okay? Now I plot the same solution on the scale of the interface. So here I only plot part of the range in U. So you see here, oops, wrong direction. Here U varied between 0 and -1. I only plot a zoom of this region here. Okay. Then what you see is this. Here you see the center of the phase field profile. So it goes from +1 here to -1 here. And what you see is, okay, on the outer scale, it looks like the temperature field has a discontinuity in slope, which is precisely what the Stefan condition would predict you. Remember, the Stefan condition was V times L is equal to the difference of -d grad U in the liquid plus d grad U in the solid. So if you take this at face value, of course, since V is finite here, that means that there's a jump between the gradient of U between the solid and the liquid. Okay? That's exactly what you see here. Oops. The gradient is 0 here and has a finite value here. Okay? In reality, if you blow this up, you see that there is no discontinuity in the slope because the slope varies continuously between the two values on the two sides of the interface. And why is this the case? You see, this condition is obtained under the assumption that all the latent heat is released at an infinitely thin interface. Here the latent heat is released wherever the phase field varies. So this heat source term is smeared out over the whole interface. It's diffuse, and therefore this change in slope is also smoothed out and it takes place gradually. Okay? Now, what are the red lines? The red lines is an illustration of this asymptotic matching procedure. So you see, I have this structure inside the interface, and I have this structure outside the interface. Now what I can do, is I can go in the outer solution and fit some asymptotes to this solution. So you see this can be fitted by a straight line, and this here can be fitted by an exponential. That's my outer solution that I can calculate. So I fit this straight line and exponential to some part of the solution that is close to the interface, but outside of the interface. And if I plot these asymptotes, that's the two red lines. And you see, if I prolongate these asymptotes to the interface position, here 0, you see that I get some value. And this is the boundary condition that the outer field sees. Okay? So this value of the crossing of the red line with the interface position, this is the effective boundary condition that is imposed on the outer field by the phase field. Okay? And you can see that this boundary condition actually depends on the structure of the temperature field inside the phase field, inside the interface. So it's a non-trivial calculation. You have to solve this inner problem, and you have to calculate the entire solution for this temperature field in order to get the right boundary conditions. Okay? So just to come back to these formulas that you obtained, there's one very important point. This here is the expression for the capillary length. So in some sense, this is a sort of strange way of writing the Gibbs-Thompson condition, because the capillary length contains the surface tension, okay? And this relation is actually quite easy to obtain. You can obtain it by the type of simple calculations that I have done with you for the Cantillard equation and for the Alencon equation. That's not much of a problem. The real difficult part is this one, for the kinetic coefficient or for the interface mobility, because you see that this expression has two terms. Okay? Now, where do these two terms come from? You can exactly understand their physical origin. The first one here, this is exactly the same that we got for the magnetic model. That is, this is the drag force that you get when you put a homogeneous driving force. Okay? So if you put a homogeneous magnetic field, that's what you get. Now, what's the second term? The second term is actually quite interesting and quite non-trivial, because you see, in reality, the temperature varies across the interface. Okay? I have told you that the temperature determines the driving force for the phase transition. So you see that actually the driving force is not constant through the interface, it varies through the interface. Okay? So in order to get an exact value for this interface mobility, I told you that the interface mobility is the constant of proportionality between driving force and velocity. Now, if your driving force varies through the interface, you have to take this into account in order to get the right constant of proportionality. Okay? And that's exactly what that second term is. It takes into account the fact that the driving force is not constant through the interface. And the important point here is that this variation of the driving force is actually created by the diffusion of the temperature. That's why in this second expression here you have the diffusion coefficient, the heat diffusion coefficient that appears. Okay? So this is actually a really nice formula. Why is that? Because you see, you have two terms of opposite sign. So if you choose your model parameters right, you can arrange them such that this is 0. So you have a 0 kinetic coefficient, which means that you have like an infinite interface mobility. And this is often a very, very good approximation for metals because they have very fast interface kinetics. If you don't have the second term here, you only have the first term. This one is always positive. So if you want to have a small interface kinetic coefficient, that means you have to choose an extremely small relaxation time, which means that your equation is very stiff. So it's very important for the model performance to have this term. And this term was for the first time calculated by Karma and Rappel. So in Alan Karma's group in Boston, so this was in the end of the 90s. This was a true breakthrough So here you see some figure of their big paper where you can learn all of this from 1998, where they test whether this calculation of beta with these two terms corresponds to what you see in simulations, and what you see, what they call old sharp interface limit, that would be just the first term. The new thin interface limit, that's the expression with the two terms, and you see the full line is the simulation, and you see that really it agrees with this expression with the two terms, but it's the old expression is completely wrong. So it's really, really important to take into account these inhomogeneities of the driving force within the interface. Okay, well, I think I will skip anisotropy here because I'm already quite late. I just want to show you a dendrite. So here I'm going to simulate exactly the situation that I've presented to you before. Here's a small solid nucleus that will grow in the liquid. And anisotropy is important for dendrites. I have mentioned this. And you can incorporate anisotropy quantitatively in the phase field model, either by having the gradient coefficient depend on the orientation, or by having the interface mobility depend on orientation. So I think you will have a tutorial about how to do this in practice, so that's why I can skip the details. The normal vector can be expressed by the gradient of the phase field, so everything is in closed form. What you have to be careful is if you introduce new dependencies on the normal vector in the free energy functional, you have to recalculate the variational derivative because there will be new terms there. Okay? But if you incorporate this, then you can get the growth of a dendrite. And so this develops, ooh, okay. So this nicely develops the full dendritic structure. So this is the 3D calculation, so there is a little bit of coding for the equations of motion and for the boundary conditions. But you know, you can get this dendrite from a Fortran code with 300 or 400 lines. So it's really not very complicated. Okay? So equally from a C code with 300 and 400 lines. So if you think about how to do this with a sharp interface code, you multiply by a factor of 100 the number of necessary lines, I think. Okay, so this is a dendrite. Once again, anisotropy is important. So here's what you get when you switch off the anisotropy. So it's not a good idea. All of this can be made quantitative because, so here is, I've told you the speed of the dendrite tip after a transient settles down to a constant speed. That's what you find in the simulations. Our simulation is the black line. The red dotted line here is a prediction of what is called solvability theory that predicts the steady state dendrite tip velocity as a function of the anisotropy, and you see that we very nicely converge to the predicted value. So the model can quantitatively describe dendrite growth. Now there is a very important point that is given by this, it is illustrated by this graph. And now I need to go a few slides backward. Nobody has protested when I showed these expressions, but you should have protested. Anybody find something strange about these expressions? If you look up here, what do you see? What's the problem? Or what's funny here? Well, you have two physical parameters that you should describe. How many model parameters are there? So is the choice of the model parameters unique? You have two quantities to match, so you have two equations, but you have three parameters. So answer, the choice of the model parameters is not unique. Or in other words, there is a whole family of models with which you can simulate the same free boundary problems. Now, how can I understand this? Well, there is one very intuitive way to understand this. You see there are three parameters. This is the relaxation time of the phase field. This is the coupling constant. But there is one that has an obvious meaning. This W here, this is the interface thickness. It's the square root of K over H that has appeared in several times. So if you have one free parameters within these three, you can see this as if you have the interface thickness that is a free parameter. So in other words, you can simulate these free boundary problems with various phase field representations that have a different interface thickness. Okay? In other words, if you smooth out this free boundary problem, you can decide how much you smooth it out. So you can choose an interface thickness. Once you have chosen this interface thickness, the other parameters are fixed. Okay? Right? So, why is this essential? This is essential because I have shown you this nice molecular dynamic simulation of a solid-liquid interface. So you have seen that the real interface is diffuse, but its thickness is 2 or 3 atomic layers. Right? If I have a hyperbolic tangent that has as a characteristic thickness this scale, which means 1 nanometer, you have seen in your tutorials your discretization has to be of the same order of magnitude as this interface thickness. So if I have to discretize on the scale of 1 nanometer, I will never be able to simulate a dendrite that has a scale of microns. Okay? So if I want to do calculations like the one I have shown and match this to anything that is interesting in metallurgy, necessarily I have to use interfaces that are much thicker than the physical ones. Okay? Now, if I want to do this, I need to know how to do this properly. And precisely this procedure of matched asymptotic expansions gives the answer to this problem. By these formulas here, in some sense, you can use interface thicknesses that are much thicker than the real ones and still get quantitative results, because these formulas tell you, if I use an artificially large interface, how I have to choose the other model parameters such that I still reproduce the good free boundary problem. Okay? And so the plot that I have shown you at the end was again extracted from this historical paper. So they calculated the dendrite in 2D, and what you see here is the characteristic plot that you should always seek for if you want to assess the quality of a phase field model. Here are various values of the interface thickness. So this is a test what dendrite tip speed you get for different interface thicknesses. So here they chose different members of that big family of models that can simulate the dendrite. And you see here, if the interface thickness is small enough, they get fairly consistent results. That is, they get approximately always the same velocity. If the interface thickness gets too big, well, then you get results that are off. And how can I judge if the interface thickness is too big? Well, the answer again comes from this matched asymptotics procedure. This procedure is only valid if my interface is much thinner than any other length scale of the problem, because only then this two-scale approach with the inner and the outer region is legitimate. So I have to compare the interface thickness to other characteristic length scales of my problem, for example, to the radius of curvature. So my interface thickness has to be much smaller than the smallest radius of curvature, and it has to be much smaller than the diffusion length. In practice, what we found for a dendrite, the smallest radius of curvature is at the tip, and we found that for interface thickness of the order of 1/10 of the tip radius, the dendrite speed is fairly well converged. Now, if you think about what that means for a dendrite, which has a tip radius of 10 microns, that means that you can use an interface thickness of 1 micrometer instead of the natural interface thickness of 1 nanometer. Okay? So you gain a factor of 1,000 in interface thickness. Now, I invite you to very briefly think about what this means for a calculation the one that I have shown to you, that is a 3D dendrite. As I have said, the discretization that you need is proportional to the interface thickness. If I'm on a three-dimensional regular grid, if I gain a factor of 1,000 in the interface thickness, that means that I get a factor of 1,000 to the cubes in the number of grid points that I need. Okay? Then the time step normally is also related to the grid spacing. We have heard this already yesterday. Time step usually is like the grid spacing squared. So if I can increase the grid spacing, I can also use much larger time steps. So I gain another factor of 1,000 squared. So in total, I gain a factor of 1,000 to the 5th power, which means 10 to the 15 in computational speed, just by the mathematical calculation. Without any modification or complications in the numerical algorithm, I think that's a really nice gain. To gain 10 to the 15 just by some mathematical calculation. And this is exactly what makes quantitative phase field calculations possible in solidification, the fact that you can do this interface upscaling. Okay? So, yes, I will stop here. Actually, what I wanted to do was to talk to you also about alloy solidification. I will just, yeah, I can do this tomorrow, but just to give you the main idea is to exploit this analogy that I have mentioned several times today. If I'm in an alloy, the relevant thermodynamic potential is the grand potential, and the variable that would be equivalent to the temperature is the other intensive variable, that is the chemical potential. So if I write my alloy phase field model in terms of the grand potential and the chemical potential, the equations have exactly the same structure than the one for the thermal model that I have developed here. Okay? So there is not much new in principle. It's just that you have to think through the whole thing again in different terms, but Abik is right, I can do that tomorrow. Okay? So I will stop here. I think, yeah, then I don't have a conclusion. In any case. So to resume what we have seen today, so I have told you how to construct phase field models for solidification and how to construct this phase field model in the top-down perspective that is as a representation of the free boundary problem. What is the motivation for that? Is that we have seen at the very end, if I do the bottom-up approach, that is, if I write a model that corresponds to some microscopic reality, it will be completely useless for practical simulations because I will be stuck with interface thicknesses that are of the order of 1 nanometer. And in order to be able to properly work with interfaces that are much larger, the tool to use is this much asymptotic expansion techniques, which is kind of complicated. If I want to do the calculation that gives you the magic formula, it takes about 15 pages. It's complicated. It's a double perturbation series with matching boundary conditions. I had to work a few weeks to get it right, to reproduce it. I mean, it was Alain Karma who did it first. I was very much implied for the alloy models, but even for the thermal model, it's not so easy. You need to make your brain think hard and get some advice from mathematicians eventually. So it's not easy, but when you can do it, it gives you a really huge benefit. And actually, this has made quantitative applications of phase field models in solidification possible. So this paper of 1998 by Alain Karma is a really breakthrough. I think by now it's cited 1,000 times, and it deserves to be cited 1,000 times because it has really opened up a whole new perspective for phase field models. And that's what I have tried to tell you in this course of today. Okay? So I think this afternoon you will code the simple phase field model of solidification that we have seen, but without anisotropy, right? Okay. So of course, if you have questions, I'm here. And otherwise, we'll meet for the last time tomorrow, for the last course. No, I'm going to meet for the last time, the last course.
So, yes, this quantitative rate, is it valid in both low energy and
Ah, okay. Yes, I took out that slide. Yes, it's valid in both limits. It turns out that when you are in the high undercooling limit, in fact, this term doesn't, it's this term that is dominant. Okay? And so in the high undercooling limit, actually, so I have told you, in metallurgy, for slow solidification, beta is approximately 0, or the interface mobility is approximately infinity. Now, if you go to very fast solidification, like for the nickel dendrites, then this is not true. Okay? Beta has a finite value, and it's important to know the interface mobility. Now, it's really very hard to know the interface mobility from experiments. So what we did is we collaborated with people who did molecular dynamics simulation. So they did molecular dynamics simulation of nickel interfaces, so the growth of nickel dendrites in pure nickel. And so they extracted values of this mobility for us. And then we used this formula, and I said, so then you have to have a finite value of beta. And it turns out if you have a finite value of beta at high growth speed, you can forget about this. Is this who determines this relation. But you can properly fix your model parameters. And let me see. I don't know why I took out this transparency. I can find it certainly. Can I find it here in another talk? Yeah, here. Yeah, but the one on the nickel dendrite is this one here. So this is this case of pure nickel dendrites. So we collaborated with Mark Asta and Jeff Hoyt, who did the molecular dynamics calculations. So what they did is they extracted the value of gamma and mu for us for various orientations. Then we put this into our phase field model and used this asymptotic calculation to fix the model parameter. So we have a quantitative representation of these values, gamma and mu k, that were given to us. Then we did simulations, and we compared to the experiments, and our simulations are the black points, and the white points are experiments. So we were very happy, because if you believe molecular dynamics, this is a test without adjustable parameters. Right? So this is a proof that this can work quantitatively if you have the information about the interface properties, that is the surface tension and the interface mobility. There is a quantitative way of fixing the phase field model parameters, and so you can trust what you find. So this is the comparison of this simple data that I announced. So this is the growth speed as a function of the initial temperature of the melt. So we can match this for a concrete substance, which is nickel. There's various ways of arguing, but it turns out that, yes.
Any more questions?
Okay, then see you tomorrow. No, tonight this is not possible because we are going out. So either it can be in the late afternoon. So when are we going to leave in tonight? So the tutorial will go until 4, right? Is there any time we meet your colleague there with the solid state dendrites? Was any after 4, yes. So maybe